Okay, the first video I'm going to do is a teaching guide to the slideshow on ionic compounds, which I got the sense during class a lot of people had not actually done the notes on yet. Considering how time consuming this topic is, that was a very concerning thing. So let's do some run through of how the steps are outlined for you in this slideshow and some important points that you're going to need to know by the time you take an exam on this, but not necessarily for your quiz that's coming up on naming. So there's a little bit of recall here because the entire other slideshow is just for molecular compounds. Molecular compounds, just to be clear, are going to be only binary for you right now, and they are going to contain no metals, which is why it's very important that on your periodic table, even without a color-coded one, you know where the metals and the nonmetals are, so you can determine quickly if an element is a metal or a nonmetal, so you can determine which naming rules you're going to use. So the rest of this um, slideshow is going to be about ionic compounds, but a lot of time is going to be spent on the next video, which is the skills video, differentiating between the different compounds so that you're using the correct rules when you're naming them. Okay, so this slideshow under ionic only covers the rules for ionic naming. So it's very important that you recognize the difference between these compounds based off of their names, as well as based off of how many elements are in them and what types of elements are in them. Okay, so there is a big slide here which tells you also what are the categories for the different elements, and compounds. So on the left, you can see that there are categories for elements. The categories we use to classify elements. So please don't forget the term classify means to put something into categories. Your categories for elements when you're classifying are metals, nonmetals, and metalloids. You're going to notice that in order to keep you from being confused, we're going to be sticking to compounds that strictly contain metals and nonmetals right now. There is a more detailed way to figure out if a compound is covalent slash molecular, which those are the same thing, or ionic, which is the opposite thing, based on a different set of criteria, but we're not going to get into that until next quarter. So for right now, we're going to stick with elements that you can compounds you can tell by the classification of element or the number of elements. Okay, and then here's your classifications for compounds. If you're classifying compounds, they go into one or two categories. That is ionic compounds or covalent compounds, which are known also as molecular compounds. And that is because they form molecules. We'll get deeper into those definitions later. Just keep in mind that these are the same thing. Okay, so if they ask for covalent or if they ask for molecular, they're talking about the same thing. You can also use those terms interchangeably. So if on a question you say, oh, this is a covalent compound, or you say this is a molecular compound, you're going to be correct both times. I'm not going to get too far into this right this second. Ionic bonding does involve a transfer of electrons between atoms, but we're going to get much, much deeper into bonding third quarter, so we'll focus more on that. I just wanted to start exposing you to these definitions so that you know what's going on. This is a huge deal, this slide. So if I've already droned on and you're starting to fall asleep on me, pause the video and wake up. This is really important. People start to pick up on the fact that a lot of ionic compounds contain metals. So sometimes they oversimplify the rules and they believe that all the ionic compounds contain metals. And I'm here to tell you that's not true because, especially when there are polyatomic ions involved, you could find that compounds don't contain any metals. So the only way you're going to be able to tell that those are ionic is if you count the elements and you see that they're not binary. So I want you to make sure that you're not fixated on this. Yes, it is true that if you see a metal, you can immediately assume a compound is ionic. But just because you don't see a metal doesn't mean that it isn't ionic. You have to also check to make sure it's binary. So I used to teach this the traditional way where everybody does one category at a time and then we slowly add on. And I found that what ends up happening is kids start to fall into these patterns and then they start making mistakes as more complicated compounds come up. So right from the beginning, I basically gave you all the types of compounds at once so that you wouldn't fall into this trap. Okay, so I'm not going to get into the reasons why people bond. We're going to do that at a later time. It's important for you to be familiar with it just in case it comes up in a multiple choice question. Um, but let's get down to this definition of what an ion is. So it's pronounced ion. It's a Greek word, and it is defined as any particle that has a charge. So that can be a single atom or it can be a group of atoms. And that's why there's a separate slideshow just to talk about polyatomic ions, which is a group of atoms that have picked up a charge and they travel together. They come as a set. Okay. So here's the basics of how ionic naming works. Much like molecular naming, the first name stays the same. Okay. In molecular naming, you'd be allowed to put a Greek prefix on it. In this case, you're not going to do that. Only molecular compounds can get Greek prefixes. You may never, I'm going to repeat that, you may never use a Greek prefix on an ionic compound. Okay, so this is going to be hard at first. If you're not taking the time to first check what category you're in, you're going to use the wrong naming rules. Okay, the second part of an ionic name, so technically this first one that I have in light blue, this is going to be the one that's considered to have a positive charge. It has a positive charge. When you memorize your charges, you're going to notice all the metals are positive. A couple of the nonmetals sometimes will do positive charges, but not very often. The second name in an ionic compound or the second element in the formula will be the negative ion. Now, this is based on the idea that opposite ions are going to attract to each other like magnets. So, this second name, just like in molecular naming, picked up an IDE ending. So, this is going to look very similar for the nonmetals on the second part of an ionic compound. Okay. All right. I'm not going to get too far into this right now because I want you to focus on the rules. But generally speaking, you can actually get into why did they pick up negative and positive charges. We're going to get a lot deeper into that next quarter. This is the very first thing I asked you to memorize besides your elements, which is you need to be able to label your blank periodic table when you get to class for Tuesday's quiz with these charges. And that's so that you have them handy because your table's not going to tell you anything else. So you have to know what are the common charges for these groups. Now, there are also going to be elements that have the ability to take more than one charge. Those are going to be marked for you because they have a separate rule for them. I know this sounds complicated because there's a lot of rules. Okay, so if you're dealing with basic binary compounds, binary ionic compounds, these charge rules, the very easy one to memorize, are going to get you by most of the time. Just don't forget, you're going to notice a big gap right here. See, it goes group 1, group 2, and then all of a sudden you're on group 13. Okay, you're skipping groups 3 through 12 because it's mostly the transition metals who are going to have confusing charges and who are capable of having multiple charges. Whereas group 1 and group 2 elements, a lot of the group 13 elements, they're only going to be able to have one charge. That's why I have to mark them for you because there's a couple of exceptions to this rule. I did actually just look this up. I was trying to figure out how did I memorize it without a periodic table with the charges on it. And just generally, the rule is that if it's a transition metal, it's probably going to need Roman numerals in the name because it probably can have more than one charge. Now, you can get very specific about it because there are a couple of transition metals like zinc, titanium. They don't only get one charge. Silver does it. So you don't actually have to use Roman numerals on those, but you're not wrong if you do. So there are 3 people who are post-transition metals who are underneath the staircase: lead, tin, and bismuth. They can pick up 2 different charges, and so those guys are going to need Roman numerals. So I will mark them for you. Okay. This is some general knowledge. Positive ions are known as cations, and negative ions are called anions. We'll come back to that. But let's talk about these actual rules. So first things first, let's talk about simple binary ionic compounds. So what makes it binary? It has 2 types of elements. What makes it ionic is if you only see 2 elements, there's definitely going to be a metal there if it's ionic. Okay. Um, they're going to be pretty much the main group metals, which means anybody from group 1, anybody from group 2. So we're talking like sodium, potassium, magnesium, calcium. Um, if they contain transition metals, they have multiple charges, so that adds on an extra rule. But those are still binary compounds. So an example might be, sorry guys, I still can't find my stylus. An example might be like sodium chloride. That's a binary compound that has sodium, which is a group 1 metal. But I can also do it with a transition metal, right? I can have copper chloride too. So the first time you're going to see this come up where you're going to have to use Roman numerals in the names is going to be with binary compounds because they're not always with polyatomics. They're often with binary compounds as well. All right. So you should know that metals are always going to be positive. Some of the non-metals are going to do some funky things sometimes, but you're not really going to run across it as much in our situation. Most of the time, if you see non-metals in the beginning of a formula, it's going to be molecular anyway. Remember, molecular compounds don't have charges. So don't start balancing charges for molecular compounds. Just follow the Greek prefixes that you see. Okay, if it is a regular metal, you always write it first. If it is a group 1 or a group 2 metal, you're going to go with a +1 or a +2 charge. If it's a transition metal, you may see if the name is written out that it has a Roman numeral to indicate what its charge is. And the anion is always going to be written second, and it's going to pick up that suffix IDE just like we did before. So don't forget the next thing you have to memorize. So far you're memorizing your charges. You're memorizing the Roman numerals because you can't confuse 4, 5, and 6 in the middle of a quiz. You're going to get your charges wrong. So make sure you know your Roman numerals up to 10. I will tell you most of the time, there's no elements really that get charges over 7. So I would probably go up at least to 7. Make sure you know 7. The basic pattern here is one line represents one number until you get to 4, where Roman numerals do this weird thing. Here's 5, right? 4 becomes 1 before 5, and 6 becomes 1 after 5. And then that's what happens for 7, 8, and 9. But 9 becomes 1 before 10. My general sense here is that this has something to do with the fact that even though Romans had paper and stuff, they did a lot of carving in stone. So I think that this was just easier to carve and to write because it didn't require any curved shapes. You could just write lines. Okay, so let's practice a couple of these. These are some simple ionics that are binary. And so the names are very easy. Naming them is very easy. You just put the positive ion and the negative ion. Okay, on this particular slide, you're going to see there's a list of ones that I know kids have trouble with all the time, just to help you know where does the ending of the element come off and where does the "ide" go. Okay, so this is going to be potassium. Just say the name, no Greek prefixes. This is ionic, you're not allowed. Okay, potassium. And then the second one's going to get the IDE ending, potassium oxide. Okay, this is sodium chloride, magnesium oxide, sodium oxide, magnesium chloride. Very easy, right? As long as it's a group 1 or a group 2 metal, it's going to be really super easy for you to do these. So naming from a formula is probably the easier step in naming binary ionic compounds. It's going in the other direction that's a little bit of a pain in the ass, okay? And that's why you have to memorize these charges. When you're going from a name to a formula, that's when you have to look up the charges for each one of these and balance them in order to write the formula correctly. This is why I don't need Greek prefixes, because if you go back, you could see, right, that, for example, here's sodium oxide written out for you. Sodium has 2 sodiums on it, but you didn't tell me that, and that's okay with ionic compounds. Because when I get over here and I do the balancing, I'm going to go ahead and look up the charges, and then I'm going to see that they're not adding up to zero. So remember, we're playing this game where the charges have to add up to zero. And the rule is, in order for me to get that to work, I have to bring another player to the table. Okay, so I'm going to put two sodiums. I'm going to put sodiums until I get the charges to balance. Okay, and then at that point, if I have two sodiums, I can get the charges to balance out to zero. And that's how I know that the formula is going to be two sodiums and one oxygen. And that's why I don't need Greek prefixes, because I'm going to be able to figure it out without you telling me how many are there. Okay, so for potassium bromide, same thing. Potassium has a +1, bromine has a -1, so my work is done. That all rhymed. Sorry, I didn't mean to do that. Magnesium iodide, Mg has a +2 charge. Look it up right now, it's in group 2. Okay, iodine in group 17 has a -1 charge. Everybody in group 17 commonly picks up a -1 charge. So if I have a +2 and a -1, I'm going to need, so here I am, and this is group 17. I'm going to need a second iodine to balance out the charge on the magnesium. So that's going to get me MgI2. Okay, so people get confused about the difference between this number and this number. Remember, subscripts count atoms. These ones up on the top tell you charges. You are using the charge to figure out how many atoms you need, but these numbers are not going to be the same. So I'm counting how many iodine I had to put. I had to put 2 iodines to get the charges to balance, so that's why I'm putting a 2 here. Okay, so here it is written out for you again. Here's the steps. Write the charges out. Check to see who you have to add to win the game. Go ahead and count how many atoms you added, and that's how you write your formula. Okay, so the transition metals, let's get over to our Roman numeral problem. So this is very common with kids who don't study very well, is they don't put the time in, so they don't actually understand why they're doing different things. And so for like over a month or 2 months after this, you'll still be saying to me, I don't understand where the Roman numerals go. Why are there Roman numerals on some of them and not on other ones? And it's because you just didn't study. Okay. I clearly said to you, Roman numerals are for transition metals. Any metal that has more than one option for its charge, you have to tell me in Roman numerals, but only in the name. Okay. In the formula, I can reverse engineer the charges and figure out what charge is on the transition metal. It's when you write the name that it becomes a problem. When you write the name out for me, if it's a transition metal and has more than one charge, and then you go to write the formula, you're going to need to balance the charges to write the formula like we were doing here. If you don't know which charge to use, because there's more than one charge there, you're going to get kind of stuck. So in the name, you have to use a Roman numeral to tell me what the charge is. Okay, now this is actually not the original way that it was done. This is known as the Stock system, and it was invented by a guy named Alfred Stock, and the man is a genius because the way they used to do this would make you cry. Okay, they used to make you memorize a separate name for every element according to its charge. So it used to be like copper with a +1 was cuprous, and copper with a +2 was cupric. And you had to name things according to all these extra things you had to memorize. So, like, seriously, you think you're memorizing a lot now? Now imagine you had to memorize up to 4 extra names for each element where the ending changed based off of its charge. And Alfred Stock, I'm oversimplifying the story. I don't really know the story of how he did this. At some point, he was just like, hey guys, maybe we should just write a number for which charge we're using. Genius, right? Like, just make this simple. Instead of saying cupric or cuprous, if you're using the copper with the +2 charge, why don't you just write a Roman numeral 2 after it so I know what charge you're using? Duh, right? Total genius. Okay. So these are some of the exceptions. Everybody who's a transition metal, you're pretty safe using a Roman numeral for them when you're writing their name. But underneath the staircase, you're going to notice that there's 3 other elements. This is tin, this is lead, and this is bismuth, and they have additional charges. And so you're going to need to use Roman numerals for them as well. All right. Now, what's the deal with this? Does it matter whether or not a transition metal has one charge or the other? And the answer is absolutely yes. Okay, if I don't say which one I mean, I actually am talking about two totally different compounds, right? If I go to do iron with a +2 charge and I tell you it's iron and oxygen, iron oxide, when I go to balance the charges to write this formula, I'm going to get one iron and one oxygen. That's this compound, which is black. It's a totally different chemical because I'm going to get a different formula with different subscripts. If I have an iron with a +3 charge, the charges are going to balance differently. And so I'm going to get actually a different formula. So here the formula is FeO. Let me do annotation. This is the formula for this compound. And this is the formula for this compound. These are two different chemicals. So this is just like when I said to you, if it was a molecular compound, if it's H2O, that's water. But if it's H2O2, now it's not water anymore. Now it's hydrogen peroxide. The same thing happens here. So I have to know which charge you're using so I can get the formula of the correct compound. And I put pictures here for you so you could see. They're not the same thing. This is rust. And I mean, it can be used to make red pigments, but this is the black version of iron oxide. It's a really common pigment. Pigments are things that are used to make color. They're not quite the same as dyes. Dyes are usually like organic. These are inorganic and they make colored things like colored paint. It's used very commonly in eyeliner and mascara, and it's used to make pen ink. And it's been used for hundreds of years actually to make ink to write with that you dip things in like a quill or a nib pen. So these are two different chemicals. So this is why, see how the Roman numerals here? This Roman numeral, oops, sorry. This Roman numeral is indicating to me that it is, this means iron with a +2 charge. Okay. And this means iron with a +3 charge. That's what that Roman numeral means. Okay. You have to tell me which one you're using when you're writing the name. Otherwise, when I go to balance the charges, I won't know which one to use. I won't know if I'm getting the formula right. So this, I often say to people, like literally, if I sent you into my chemical supply closet and said, hey, go get me the iron oxide, you would come back with 2 bottles and they'd be totally different chemicals. So this is why we have to be really specific when we write names and put Roman numerals in them. Okay, so these guys, when you're going from the formula to the formula from the name is going to tell you already what the charge is going to be. So this is kind of doing it in the easy direction. Okay, so it's going to say iron with a +3. You're going to do +3 when you balance the charges. This is a trickier one to balance because when you have charges that don't balance easily, you're going to have to bring them to a common number. I may avoid putting these on the quiz at first because you really have a lot to juggle right now, but expect that by the time the test comes, you need to know it. And you're going to do the same thing that you would normally do. You're going to figure out how many you need to get it to go to 0, and then you're going to count and write your formula. Okay, now it's going in the other direction. That's the problem. You have to recognize that you need to put a Roman numeral in the name. If you're looking at a formula and you're supposed to name it, you have to know that that metal is coming from a part of the table where you need to put a Roman numeral. Okay, so we're going to keep the training wheels on for this quiz. I am going to mark them for you, but I'm not going to give you the charge. How come I'm not going to give you the charge? What kind of horrible person am I? It's because you're going to be able to reverse engineer it. So here's a picture of me reverse engineering the charge, right? It says that there are 3 oxygens, so I write out 3 oxygen. Each oxygen has a -2 charge. That's adding up to a -6. I know that the rules say I got to get to 0. That means that whatever is attached to this is adding up to a +6. Okay, I have 2 of them though, so whatever this charge is, it has to evenly distribute. And I know I have 2 of them because I have the formula. So I'm going to go ahead and give each of one of these half of that charge. That's a +3 charge. So when I write the name, I write iron with a +3 charge in Roman numerals, and that's how I write the name, iron 3 oxide. Okay, it is complicated. There are a lot of extra steps. Okay, so it is true that like 90% of the ionic compounds you're going to see are going to contain metals, but some of them don't. And so here's a warning about some of the most common ones you're going to run across that are made of polyatomics or contain a polyatomic, and that's what's making these ionic. Okay, so a compound that contains ions is an ionic compound. So this is why I want you to memorize your polyatomics. Okay, so don't forget, I would like you to memorize 6 of the polyatomic ions. This goes a little bit into what polyatomics are, but these are the ones I want you to memorize. So sulfate, carbonate, ammonium, nitrate, phosphate, and hydroxide. And these 6 are the most common ones you're going to run into. I especially want you to memorize hydroxide, but when you take your quiz on Tuesday, there will be compounds with polyatomic ions on them, and I'm not giving you the table. I know you guys like whine about everything. You're complaining already that I'm making you memorize 6 polyatomic ions. I had to memorize 30. Okay, in college, if you go into a STEM major, you have to memorize a lot of stuff. If you don't have that basic knowledge at your fingertips, there's no way for you to do high level work quickly, right? Just like we talked about in the beginning of the year, this is fluency. If you're not fluent, you can't speak the language, right? If you don't not doing your basketball drills, you're not going to be able to play well during the game, right? This is like a form of rehearsal and practice that makes it so the more difficult stuff comes more easily. And if you have any intention, and don't you dare quit just because you think, oh, geez, well, being a doctor will be hard because I'll have to memorize thousands of things. That's not a good reason to quit on being a doctor. Okay. This whole like idea that you shouldn't have to work hard to do a job. We won't have any doctors left. Can you guys get over that? So you have to be able to be fluent in things in order for you to do your job well. So this is just really good practice. Once your brain gets the hang of this and you find the tricks that work for you, you're going to find that this really helps your thinking process and improves your confidence. So please, please, please memorize these 6 polyatomic ions, particularly hydroxide, but you're going to need to know all of them. And this is why I'm telling you, I've tested this out. I've been at YMA for this is my 9th year. Okay. I've had years where I made kids memorize stuff and years where I didn't make kids memorize stuff. Guess what? My kids who memorized stuff did better. My kids who didn't have to memorize stuff, they were still confused. They were still scrambling and looking through the reference table because they didn't know how to use things. They didn't know which things to use. If you memorize it, you're not going to be confused. If you memorize it, your reference table becomes a better tool. Okay. So when you're naming stuff with polyatomics, it's actually super easy. It only gets tricky when you run into a transition metal. Okay, so this is the full table E. Later on, when I give you other polyatomics that I didn't make you memorize, I am going to give you table E, but there will be a transition period where I will take the ones that you're supposed to memorize off the table. I'll delete something, like I'll take their names off, but not their formulas, stuff like that. Okay, so that you have to look them up and you really understand what they are. Right, so an easy one would be somebody who has a regular metal like sodium, no Roman numerals involved because it can only have one charge, so no Roman numeral. So this is just sodium sulfate. Same thing with calcium, it's a group 2 metal. So group 2 metals always have a +2 charge, so I'm just going to say calcium carbonate. I know that the charges are balanced because that's the rule for writing formula. So if the formula is already here, I know these charges are already adding up to 0. Okay, this is where it's going to get tricky because iron is a transition metal. It's element number 26 in the middle of groups 3 through 12. Okay, so iron is Fe. It is one of the elements that has a Latin name. Its Latin name is ferrous. Sometimes people say ferrium. So this has to have Roman numerals. So I'm going to reverse engineer my charge. So if I look at sulfate, I memorize sulfate. I know sulfate has a -2. It must be balancing out with this iron. So this iron must have a +2. So when I write the name, I'm going to put iron Roman numeral 2 sulfate. There is a possibility it could have a +3 charge, but if that were the case, the formula would be written so that those 2 charges were balancing and I'd be able to figure out that it was a +3 charge. Okay, and now this is one that I didn't ask you to memorize. It's over here. See, there's a whole series of them that have chlorine in them. So I look it up on the table. This is chlorite. So I'm just going to write sodium chlorite. And I'm going to assume it's balanced because it is, right? Once the formula is written, the charges go away because they are canceling each other out. All right, now let's go in the other direction. This is a little trickier. So in order for me to do this direction, I have to make sure that I figure out everybody's charge before I balance the formula. Okay, and how am I going to know to do that? I'm going to look and see that they're ionic. Okay, so these all contain metals, so it's very easy to spot that they're ionic. If they're ionic, I must balance charges before I write formulas. So I sometimes will have people who will just write CaNO3, and that is wrong. Okay, I must first check. So NO3 has a -1 charge, but calcium has a +2 charge, which means I'm going to need another NO3 here. So in order to put two NO3s, I'm going to have to put parentheses around it and then put a 2 so that people don't get confused and think I have 32 oxygens. Okay, same thing for magnesium carbonate. Mg has a +2 charge. Carbonate I have memorized, it has a -2 charge. These guys are already balanced, so I'm just going to write MgCO3. Here, I don't need parentheses because I only have one carbonate, so no one's going to be confused about what I mean. Okay, this is a transition metal, so they told me what the charge is on that transition metal. So go ahead and put a +2 charge on that copper because this means it's a +2 charge. Okay, hydroxide's a polyatomic that I have memorized, and I know that it has a -1 charge, so I know I'm going to need 2 of these to balance this out. So when I write this formula, I'm going to put copper hydroxide. I'm going to put 2 of them. I'm putting parentheses here so it's not confusing whether or not I have 2 hydrogens or I have 2 hydroxides. Okay, and potassium permanganate. Permanganate sounds complicated. It ends in ATE, which set off alarm bells for me that I'm dealing with a polyatomic, and there's permanganate right there. I'm going to look at its charge. It has a -1 and potassium has a +1, so I only need one of them. So this is KMnO4. Okay, where did I get the 4 from? It's part of the polyatomic. Polyatomics are actually very easy to work with. Just don't overthink them. Okay, they come as groups. They just always look like that. There's no changing them. You don't have to take them apart or figure anything else out about their charges or anything right now. Okay, so if you're doing this at home and you're going back over the slideshow does have all the answers written out for you so that you understand how to do it. Okay, so some of these charges can be confusing on table E because some of them have no number next to them. If there's no number, they mean 1. So for example, on table E, when you get it, plus, you're not going to get it this time, just remember. It's a +1. If it just says minus, it's a -1. It could be, if it's more than that, it'll say -2, -3. Okay, so don't forget that these are subscripts, and polyatomics have the same writing, but if you have more than one polyatomic, that's when the parentheses come in. Okay, so this is a practice page for you to do, and if you look at the end of the slideshow, oh, maybe I didn't. Oop, I didn't give you answers for these. I'm so mean. Okay, so I'll do them with you right now, and then that'll be the end of this video. And then I'm gonna do just practice in the next video. That'll be mixed practice. All right, so this is sodium sulfate. Again, don't overcomplicate things. Okay, in this case, it's an ionic compound with a polyatomic. You don't use Greek prefixes. There's no charges for you to figure out. Sodium always has the same charge. You just name it, sodium sulfate. Okay, this is calcium carbonate. Okay, and here's somebody we ran into earlier. This is a -2 charge on this sulfate and a +2 charge on this iron. Okay, iron, the reason I'm bothering to check is because iron's a transition metal, and so that's going to make it so I have to write a Roman numeral for him. I figured out that his charge is a +2, so I'm going to write iron 2 and I'm just going to write sulfate. Don't break these up or do anything weird with them, okay? They're polyatomics. They just come as they are. In fact, I think, you know what it is? I put these at the end because they're already in the slideshow. You have all the answers. These are the examples I just did. So I would try them without me and then go back to the answers in the other slides. So that's actually what happened here. All right, so we can end this video here. And you can head over and do the video of all practice if you're feeling ready. If you're not feeling ready, make sure you sit down. You know, I'm on a video, you can pause me. Take notes just on the video. Again, we're going to right now, you can, for non-testing purposes, for just to get ready for this quiz, you can skip some of the concept slides, which are things you needed to understand about ions and about ion balancing. And the rest you can come back to later. All right, this video ends here.